All that said, you're probably wondering why, even if we want to know this, we're trying to learn it now. Because this doesn't seem like it would do anything with systems of equations. But what we're going to see here is that the process of finding those numerator terms largely comes down to a process of identifying coefficients. And that process of identifying coefficients is very much the same as what we did in our last applied example from 5.2. So we just have to be very careful at solving systems of linear equations in terms of A's and B's and C's and so on. Where if we have something like f of x over g of x, where g of x factors very completely into things like a1x plus b1, a2x plus b2, and so on down the line to anx plus bn if it has n of those terms, then we can split that up into an a1 over ax over a1x plus b1, a2 over a2x plus b2, and so on down to an over anx plus bn, because what we have in this case is that our denominators are going to be linear, which means that the next smallest thing that we could use to describe everything is just a constant. So just call those a1s or a, b, c, d, and so on. We use the subscripts there because we might end up having more than 26 factors, although don't worry about that being a thing we'll see in this class. That'd be a little bit ridiculous. Anyway, for these types of problems, we have a process that we can follow very generally, not just for linear factors, but for most any partial fraction decomposition, where what we want to do is set up the partial fraction decomposition with the unknown constants in the numerators of the decomposition, then multiply both sides by the least common denominator, which is really just the original denominator, then, or usually anyway, sometimes it's a little bit different. Then simplify the right side. Write both sides in descending powers, equate coefficients like powers to like powers of x, and equate the constants. Then solve the resulting linear system for the coefficients, where you substitute them back in to write the proper decomposition. So I will say here that sometimes with what happens at step 5, basically the stuff after step 4, we don't always need to solve the system in the most technical way. Usually when we have these things, and especially for the linear cases, there are some nice values of x that we can just plug in if we're thinking carefully about what it is we're trying to find to get our answer a bit more efficiently. And we're going to see how this works with a pretty standard example. So first, we want to find the partial fraction decomposition of 3x plus 11 over x minus 3 times x plus 2. So for this, we have our already factored denominator set up for us, that 3x plus 11 over, this is going to be a lot of writing, hopefully my wrist doesn't cramp, x minus 3 times x plus 2 can be rewritten in terms of a constant coefficient a over x minus 3 plus a constant coefficient b over x plus 2. And hopefully seeing this example will help clarify a lot of what's going on with the process here, because I know, I went through the logic for where this comes from in terms of a lot of general things, and you see a lot of general things and a lot of subscripts, it's easy to lose track of what goes where and why. When you see it in the context of an actual problem, I think it helps lock in a bit more of like how this happens. Because what we're going to do next is try and get rid of those denominators so we're left with something that we can solve for our x and constant values. So here, what we would do is multiply both sides by x minus 3 times x plus 2. So on the left, we would have a 3x plus 11 left over, because you multiply that over, both of those cancel. Then over here, if you multiply this times that, the x minus 3's would cancel, and we'd have a times x plus 2. And over here, the x plus 2's would cancel, so we'd have b times x minus 3. And this, even with more complex cases, is what always happens up to some special varieties where we're dealing with a repeated factor, but that's what we're going to see in a little bit. So for now, we just simplify this a little bit more, so we can rearrange our system here, and we would end up getting ax plus 2a plus bx minus 3b, or grouping up our terms, x times a plus b plus 2a minus 3b, where from there you could set up a system 3 equals a plus b and 11 equals 2a minus 3b. That is, you could set yourself up a system where these coefficients have to equal that one and this coefficient has to equal those two. But the truth is, that's not the most efficient way you can go about this. You can actually be a little bit more clever here to get your answer, where what you can do is recognize that in this case up here, because of that nice linear factor, if you were to plug in x equals -2, you'd end up getting 3 times -2 plus 11 equals a times -2 plus 2 plus b times -2 minus 3. And over here, and it doesn't look very nice, but it does turn out to just be a single value 5. Here, that's a times 0, so that's 0. And over here, that ends up being -5b, or you'd end up getting that b is equal to -1. And then similarly, if we wanted to use this method to get a, we could recognize that if we plugged in 3 here, that would kill b. Or we know that we already have b and we don't have to worry about that, but I'm going to do both just to make sure you can see it in both cases. So that is, if we plug in x equals 3, I'm not going to write out what happens here because it works the exact same way. You'd get 3 times 3 is 9 plus 11 would give you 20. And then on the other side, we would have a times, well, 3 plus 2 is 5, so 5a. And then here, 3 minus 3 is 0, 0b, nothing. So we would end up getting that a is equal to 4. And you can solve the system if you want. You can solve this system that gets implied there, but this is almost always a much more efficient way to go about it, that if you have unique linear factors, and I'm going to get my adjectives in the right order, this will get you your values very nicely. It doesn't always work, especially if you're dealing with more complex things, but for this, it's quicker. So, with those answers in mind, we can get our final value here, our decomposition, that 3x plus 11 over x minus 3 times x plus 2 can be rewritten as a, so 4 over x minus 3 plus, oh, that shouldn't be a plus here because that b is negative, excuse me, minus 1 over x plus 2. Or if you prefer there, you could keep that as a plus and make that 2 minus x, negative 2 minus x, excuse me, but that's probably the more efficient way to write it, and that's what our answer would be. Or if you want to check this, you could do some pretty quick math there in terms of a common denominator. So you have to multiply this guy times that. You'd get 4x plus 8. Then this one minus that would end up being a minus x and a plus 3. So you'd get 3x plus 11. And that's the process in general, no matter what our coefficients are, no matter what we have on the bottom. If we have more terms, it would just be more of these. If we had different coefficients there, it would just be different inequalities at the end. That's how we handle the distinct linear factors case, and that's what you're going to get some practice with on your homework and your worksheet and all that fun stuff. So let's see one of the other cases. Now we're going to deal with what happens if we have non-distinct linear factors. That is, if we get repeated roots.